We're going to start off today talking about power. Power is the rate at which energy is used. So since we're talking about rate, that should tell you that time is involved, right? A rate of change in something is usually per time. So power is equal to work divided by time. So remember, work here is our way of giving or taking energy away from things, or using energy, if you will. And so the rate at which we use the energy is our our work divided by time, right? How quickly are we doing work, or how slowly are we doing work? The unit for power is watts, which is abbreviated with a capital W. Now, watts is equal to, if we look at our equation, work was in joules, time in seconds. So watt is a joule per second. Now here's a point of confusion here. We see W for work, but also W for our unit, watts. Do not get the two confused. It's very easy to do. When you see a number, for example, 30 watts, 30 W, that's 30 watts. That's going to go into the power portion of your equation, not the work portion of the equation. It doesn't go in for W just because it has units of W. Work should have units of joules. So just a very simple calculation, work divided by time. One other common unit for power is horsepower. Okay, 1 horsepower is equivalent to 746 watts. So that might be a conversion you'll need to use at some point. So here's a quick sample problem with power. So we have a woman running upstairs, and power is going to be work over time. Now the work that is done, or the energy output here, comes from two sources, right? She's going up the stairs, so we're going to have a gravitational potential energy that she gains by going up from 0. And she's also going to have some kinetic energy at the top of the stairs because of her speed. So those together are going to be our work, and then divided by time. So that's going to be mgh for our potential energy, 1/2 mv squared for our kinetic energy, divided by time. So we'll plug everything in, and our power is going to be 60 kilograms times 9.8 meters per second squared, times our height of 3 meters, right, 3 meter tall stairs, plus 1/2 60 kilograms, times her velocity at the top of 2.00 meters per second squared, divided by the time of 3.50 seconds. And this gives her a power output of 538 watts to get up the stairs. One interesting applications of these would be maybe an incandescent light bulb for power. So a normal incandescent bulb, kind of on average, let's say is 60 watts. And if we run that for 1 hour, well, power is work or energy used per time. So let's calculate the actual amount of energy used here. So power is 60 watts. It's a 60 watt light bulb. Equals energy over, well, hours into seconds. There are 3,600 seconds in 1 hour. So the energy we put out will be 60 times 3,600, which is 216,000 joules to run that light bulb for 1 hour. Now let's compare that to a compact fluorescent bulb, a CFL. For the same amount of light, you only need about a 14 watt bulb. So now we have 14 watts equals energy over 3,600 seconds. And our energy output now is 50,400 joules. So a much smaller number. If we go to an LED bulb, even more efficient, we only need a 10 watt bulb to get the same amount of light. So we have 10 watts equals energy over 3,600 seconds. And so our energy here would be 36,000 joules. Now if we kind of compare those two numbers here, right, if we take our big value for our 60 watt bulb, 216,000, divided by our CFL, that means that we're using about 4 times more power than a CFL. And if we do it the other way with our LED bulb, then we're using about 6 times as much power, just based on what type of light bulb we're doing. We're changing the amount of energy we're using by 4 and 6 times as much, and that's for just an hour of use. So kind of a good practical example of how you can use power to make decisions in life.